Hi guys, welcome to the what. So today we will see the MATLAB simulations of open loop non-isolated DC to DC buck converter. So let's get started. So what is a buck converter? So a buck converter is a DC to DC converter which will step down the supply voltage. So if we see the circuit diagram and the components, what we will see that supply voltage is given, that is V in or V input. One switching device is connected here, which is given some square wave pulses. One diode is here for freewheeling. One inductor is here. One capacitor for smoothing the output, and then our load and V output. Right. So the basic principle is like we have two conditions on MOSFET. One is on. So while it is on, so then what we will have, on means it is short circuited. So current will start moving from this battery. It will pass from this MOSFET. Now at this point, the current has an option to go towards this diode or to go towards this inductor. But it will go only towards the inductor because the diode will be reverse biased, right? So, and this will charge inductors. So plus will be here, minus will be here. It will go on. Some charging current will pass from capacitor, but the main current is this, which will go in the load. Then it will come back. And now it will go in this negative, right? So this is the condition when the MOSFET is on. This is the first condition. Now on the second condition, what will happen? This is open circuited, so it behaves like a switch. So the switch is open circuited, right? So current will not move in this particular loop. But now what we have, we already charged this inductor earlier while the MOSFET was on. So now this inductor will discharge. So while discharging, the polarity will change. So plus will become here and here it will be negative. That means current will go from this inductor. It will go inside this load. It will come back and it will free will through this diode. It will come here, right? So inductor will discharge its power to this resistor or load, right? So in the second case, while the MOSFET is off, then the inductor will behave as a battery, right? So that battery will give power to our V output or our load, right? So let's see what all components do we need here. So components are same as we used in our DC to DC boost converter in the earlier video. So the components are same. So let's start the simulation. Right. So first one that we need is DC voltage, right? So we will take this black one. Then we will need RLC series branch. This one RLC series RLC branch. We will add. Then we will have a voltage measurement device. So we will take this. Then we will have our current measurement device, this one. Then we will take a diode. So we are taking this thing. This is a power diode, the black one. one MOSFET. We will take this one. We can use IGBT as well. Then we have a triangle generator here. Both are same only. Then we will have a gain, and we will take a constant. Then we will take a logic operator, that is the comparator. We will use a relational comparator. This one. Then we will use a scope to see the waveforms. We will use a display. This one, this is the display. Then we will have power GUI. No simulation will work if we don't have this. Then ground, we are taking this one, and then one add block. Right. So we have everything that we need here. So let's get started. First, we will design our main circuit. Then we will design the control circuit. This is our MOSFET. We'll untick this one. This is our diode. Current measurement, voltage measurement, RLC branch, right? So here it is the DC to DC voltage source. Here we will put our MOSFET. Then we will take this. We will put here. I'll let you know what we are going to do with this RLC series branch. We will take this diode. We will put a diode here. Let's copy paste this. Put it like this. One more. Put it like this. Here is the voltage measurement. Here is the scope. This is the display. Here it is the current measurement. Here one ground. Now let's do the connections. So let's connect our DC voltage source with MOSFET. Then let's connect this to this thing, RLC branch. Here this will behave as a load. And this will complete our circuit. Let's connect the parallel components. Diode, one capacitor. Here it will be a voltage source here, and here as well. Here we will see the waveforms. Here we will see the input slits. Put this current measurement device here to measure the output current, right? Let's take one more voltage measurement for the measurement of our input voltage. Let's visualize and compare both of these things, output and inputs. So for that, we will need two inputs, but we will see only in one graph only, so we can compare them. We will select the layout as one, right? So this will be, yeah. So this is our main circuit. Okay. Here now we will convert this into an inductor with 870 microhenry, right? This is the design value that I have designed. Now we will convert this into a capacitor with a value of 2034 microfarad and resistance are around 10 ohms, right? So our basic circuit, our main circuit is ready with an DC voltage input of 100 volts, right? Now we are seeing a control circuit. We need to provide a control circuit to control this particular gate, right? So let's take a scope, let's visualize everything. First, let's see this triangular wave generator with frequency of 10 kilohertz, because the higher the frequency, the smoother the output voltage that we will get. Here, let's simulate for 0.06 seconds. First, let's see the output of this triangular wave, right? That's what we are getting. So we are getting a triangular wave which will start from 0, it will move till 1 and it will come back to -1, right? But what we need here as a control circuit, we can work with this as well, but a more simpler way to work with this is to start from 0.5, go up till 1 and to end at 0 only. Then go and means it will, the range of this will be from 0 till 1, right? So we have to make that. So how we can make that? First of all, let's put a gain. So gain will be of 0.5. So if you multiply a waveform, it will change its amplitude. And if we add something, so it will move on y-axis. So let's see output now. So now we can see that the whole thing shifted above 0 and now it will start from 0.5, right? So this is the final thing that we want, right? Now we will take one more constant to be compared with this particular waveform that we are getting. So here let's compare, put 1 here. Here is the relational operator. Take one multiplexer to visualize the output. So in this multiplexer, what we are having, we will have one input will be from this triangle wave and one input will be from this constant. And let's put here 2 inputs. Layout will be 2. So first one will be the comparison. The second one will be the gate pulses, right? So let's run this. Let's see what output we are getting. Here, let's keep 0.5. So we can see that whenever this triangular pulse is greater than this constant, that is 0.5, we are getting no output. And whenever this triangular pulse is smaller than this constant, we are getting some output of amplitude 1, right? So these are the gate pulses that we required. If we, so we can say that it is of 50% duty cycle, right? This is one whole cycle starting from 0.5 till 1.5. So we are getting 50% duty cycle when we are putting here 0.5. Let's see for 75% duty cycle. Let's put 0.75. So now we can see that now we are getting 75% 1, and then for the rest of the 25% we are getting 0, right? Same thing will go if we convert, change this to 0.25. So now only for 25% it will give us some positive cycle, and for the rest of the time it will not give us, right? So here we can see this is the whole cycle, but we are only getting our output in positive side, only 25% only, right? So let's keep it at 50% duty cycle and connect this gate to the output of this thing, right? So, and let's take one current measurement scope as well. We will measure the current. So let's start. So as we can see, we had 100 volts. If we are keeping 50% duty cycle, we are getting 49.37 volts, right? So why this is happening? Because according to the formula for buck converter, what we have V output, that is equal to V input into duty cycle, right? So what we have we input we have 100, and the duty cycle, that was 50%, that means it is 0.5. So V output would be 100 into 0.5, that is near to 50 volts, right? So we are getting near to 50 volts. It is 49.37 because it will depend on the value of this inductor, it will depend on the value of this capacitor, as well as it will depend on the internal voltage drop of MOSFET as well, right? So after the losses, we are getting 49.37. If we see the output, we can see that the blue line is the input voltage and the yellow line is the output voltage, which is stabilizing after some time. So no issue on that thing, right? Let's change the duty cycle. Let's say, let's keep for 0.8 for 80% duty cycle, right? So let's run this. So for 80%, we will get around 80 volts, right? So we can see here at 0.06 seconds, after 0.06 seconds, it will stabilize. Let's run this for a longer period of time so we can get a clear view on this. So now we can see that after stabilizing, we are getting both constant, right? Near to 80 volts. This is at 100. So if we keep a lower duty cycle, for example, let's say 0.2, that is only 20%, right? So we should get our voltage near to 20 volts, and yes, we are getting that as well, right? At the end, we will get around 20 volts for 100 volts input, right? So this is the complete simulation of open loop, non-isolated DC to DC buck converter. So why open loop? Because we are not giving any feedback from our output to the triggering circuit or to the DC voltage source. So if we create a closed loop system where we are giving our input as the output of our circuit, right? So it is known as a closed loop. We will do simulation of closed loop as well in our future videos, but this is an open loop. And why non-isolated? Isolated means it is electrically isolated, and this is not electrically isolated. We are connecting all this circuit using wires, right? So if we use a transformer type thing where they both of the sides are electrically isolated but magnetically connected, that is known as isolated circuit. We will do the simulation of isolated circuit as well in future videos, right? So this was the whole simulation from my side. If you have any questions, do let me know in the comment section, and please do let me know what all converters you want to see in future. Thank you.